Welcome back. In this session, we'll solve one example based on FIR system. Let's start. So let's write the example. Let's suppose a system described by. Let's suppose a system that is described by a difference equation. Difference equation is y of n is equal to x of n plus 1 plus x of n minus 1. So this is the difference equation where y of n is the output and x of n is the problem. The first part of the problem is this: find the impulse response of this system. Find the impulse response of this system. Second, is this causal system? Is this causal system? Third problem is this FIR or IIR system? Is this FIR or IIR filter or system? Fourth part of the problem is find the frequency response. Find the frequency response of this system. Fifth part of the problem is this bounded input, bounded output stable system? Be both stable system or filter, whatever filter is it, FIR or IIR. Your job is to find whether this is stable or not. Alright, so let's solve this problem first. Let me rewrite this system. Alright, so the first part of the problem is find the impulse response. Impulse response means when x of n is delta n. Alright, so the impulse response is that I will show you two days. We can also do it in frequency domain directly. I mean, using Z transform. Let me show it using this. So when I put x of n is equal to delta n, so the first part will be delta n plus 1, delta n minus 1. Now we know this is non-zero only at n equal to minus 1. Sorry, n equal to plus 1, minus 1, not plus 1, minus 1. This is non-zero, means equal to 1 at n equal to 1, and this is equal to 1 at n equal to minus 1. So we can directly write, and this response is referred as the impulse response, and we denote it by a special name, that's h of n. Alright, so we can say h of n is non-zero only at minus 1, 0, 1, and this is n equal to 0, right? So this is doing the computation in time domain. Now let me do the same thing in frequency domain. So take the Z transform of this. So take Z transform of this. This will give us y of Z will be equal to different marker. So this will give me y of, this will give us y of Z is equal to Z transform of this will be Z x of Z plus Z is for minus 1. Alright, now yz will be equal to Z plus Z raised to power minus 1 x of Z. So dividing yz by x of Z will be the transfer function of this system, and that's equal to Z plus minus Z. So h of Z is the transfer function of the system Z plus ZNX, right? So this is the transfer function of this system. Now the impulse response of this system will be simply h of n will be equal to the inverse Z transform of h of Z. So this will be the impulse inverse Z transform of h of Z. So take the inverse of this will be simply delta n plus 1 plus delta n minus 1. You can see I wrote it directly. So this is the impulse response, and as a sequence you can say this is 1 at n equal to minus 1, and this is then 0 and 1, and this is n equal to 0. So this is the impulse response of this system, right? So this is the first part. Now the second question that it asks is this system causal? Is this system causal? Have a look at this. Is this system causal? No, it depends upon the past value of the input. So it depends, sorry, future value of the input. So it depends upon the future value of the input. Present value of the output depends upon the future value of the input. So this is non-causal. So this is a non-causal system. Now the third part of the problem is this FIR, IR. Now have a look at the impulse response of this system. Is this of finite duration or infinite duration? So H of m is 1, 0, plus 1, 1, 0, 1. So this is finite duration. So this is FIR system or FIR system. Right? Now fourth part of the problem is saying find the frequency response of this. Find the frequency response. So we have already determined that H of z is equal to z plus z plus z inverse. Right? So how do you obtain frequency response from this? Just substituting or replacing z by e raised by j omega. That will be h of omega. H of omega will be equal to simply e raised by j omega plus e raised by j omega. Okay. So we can simplify this. We can simplify it. We can multiply this by 2 and divide it by 2. So this is 2 sine of, sorry, cos. Sine. This will be cos of omega. So h of omega is this. Alright, so this is the frequency response of this system. This is the frequency response of this system. So this is the frequency response of this system. Now our last question is this table. So the last question that this is asking is table. Now y of m is x of m plus 1 plus x of m minus 1, right? Now as long as x of n remains stable, sorry, constant means a finite quantity, you can check y of n is a finite quantity. So you can say as long as x of n, and we know what is this x of n plus 1 or x of n, these are the shifted versions of x of n. As long as this is finite, finite means let's suppose some quantity and this is finite. This is mathematically how we say this is quantity also finite. And then y of n means the magnitude of n will be some quantity where, because we are just adding the two externals, let's call it n1 and it will be 5. So this is how we show this is a stable system. All right, I hope you have understood the problem. Please try it 2-3 times. You'll get the idea what I have done. We have repeated this procedure so many times in unit 1 and in the previous classes. Please check it. All right, let me end this session here. There is one more way to check whether this system is stable is using Z transform. Right? If the poles of the system are inside the unit circle, you can say this is stable. Can you check what are the poles of this system? There are no poles actually. This has a pole at origin and Z equal to 0. This has a pole, but all the poles are inside the unit circle. You can say this is a stable system. You can also conclude it using H of Z. So you can, from H of Z, you can conclude it is a stable system. How? Because the poles, all the poles are inside the unit circle. Inside unit circle. How many poles are there? So this is only one pole, that is equal to 0. So this is one way to check, one more way to check whether the system is stable or unstable, or the split ion system is stable or unstable. All right, let me end this session. This finishes our discussion on FIR system. All right, let me end this session here.